Hey everybody, it's Bruce and the dog on the floor, and today we are going to be talking about vision models in Axon. Specifically, we want to talk about two of the layers that are in these layer models. One of them is the dropout, and another one is a pooling layer. Each of those layers have specific purposes, but I want to kind of help you build an intuition for what's going on. We've been working through this CFAR model, and we've actually broken it into a compiled file just so we can access it from IEX and play with some of the aspects of it. But what I want to focus on in this video is this build model. And I want you to see that there are three different parts of it. The first part builds me an input based on a defined shape, and in this one the shape is a batch size or batches, the channels, rows, and calls. So that's what my input data is going to look like. There's an input layer, and then I'm going to feed it into several video processing layers. There's one and there's two. And then I'm going to feed it into a layers whose job it is to do a linear regression. And so we could talk briefly about the linear regression first, because this is what you've already seen with the FizzBuzz model. So we take the data, which is multidimensional, and we flatten it out so that it's easier to reason about and think about in a linear regression. It doesn't expand things so far that we build a network that has too many connections and is too cumbersome to process. So by this time, we've reduced and consolidated the information in the visual processing to a point that we could just use a simple linear regression. So flatten does what list.flatten does, and there's the dense layers that you saw with the FizzBuzz game. Now these are going to be much bigger than the ones that we worked in, but in the end we're putting out a probabilistic tensor where each row has a list of probabilities for each of the categories. And that's what we want to build with this model. So I want you to notice something that's a little bit new. There's a dropout. Now this dropout is going to take the model and take pieces out of it so the model doesn't become too integrated with the features in the training data. So this is going to make the model behave better and in a more general way. So that's pretty abstract. Let's talk about this so that we can visualize it a little bit. Now we've talked about the Iota function before. So effectively what I do is I take a tensor, let's make one, I don't know, 16 by 16. And so I can pass that into nx.iota, and that's going to give me, it's going to count. And if you want to visualize what's happening there, I can throw that into heat map. .to heat map. Okay, now I've got my heat map. And so sometimes what you'd like to do is take this data and ignore parts of it so that maybe it becomes a more general solution as it does with these learning models. So there's a layer that's called a dropout, and here's what it looks like in our code. So we're going to have a dropout rate. And to make that happen, this needs to be not integers, but decimal numbers. So I'll need to normalize that a little bit. And I'm going to do it the easy way. So I'm going to take this and I'm going to nx.divide that by the dimensions. So 16 times 16. And then I'm going to feed that into the heat map. Okay, so now I have really the same intensity of the data, but it's just normalized so that all the values are between 0 and 1. And that's going to work pretty well for me in this case. But let's say that what I'd like to do is ignore parts of this image so that it's not too linked to the training data that I create. So what I'm going to do is add a dropout layer, and it looks like this. Oh, I'm going to need to require Axon. And within Axon, there's a module or namespace called layers. And so let's take a quick look at that in the code base. So I'm going to dive into the dependencies, and you can see that there's axon right here. There's the lib axon, and I have the layers right here. And I can look in here for the so there's a dropout layer. So this is just going to take a tensor for an output and a couple of options. And I'm going to specify a dropout rate. So let's see how this works. So I'm going to effectively take the line of code that I had before, this one, and I'm going to add a dropout layer right in between here. So I'm going to say axon.layers.dropout, and then I'm going to pass this thing a rate of maybe I want to drop 1 in 10. Let's see what happens to this heat map. Yeah, you can see the holes that show up in the middle of this thing. And maybe I want to drop out at a higher rate. So what's happening with our model is that we are effectively going to ignore about half of the work that we've done, and that's going to give us a much more general, much more performant model when everything is said and done. And that's pretty cool. So now I'd like to move up the chain a little bit. I'd like to talk about the rest of this. So we've kind of seen the general idea of the batch normalization. It's a more sophisticated mathematical way of normalizing the data that we have so that everything remains in a confined numerical space so that I don't get a model that is numerically unstable. But I want to talk about these other two layers. So we'll get to convolution layers a bit later. What I want you to think of when you see a convolutional layer, this is like a searchlight, and it's going to scan across all of the input image, and it's going to look for small patterns within that data. And what that's going to allow this system to do is identify individual features like parallel lines or diagonal lines, or maybe something that looks like a circle or a triangle. And these aren't features that we're going to build ourselves. These are features that we are going to initialize initially to random numbers. And if the image patterns match those random numbers, then it'll match, otherwise it won't. And obviously this isn't going to do too much good for us until we start to apply the calculus. And the calculus is going to move these features that we're trying to recognize into features that show up in our training data that we want to match. So this is going to do some scanning, this is going to do some normalizing, and then we're going to pool the data. And so one of the things that I want you to notice is that when we create this model, what's going to happen is when we scan for features, this is going to make the number of parameters large, actually too large for us to manage if this were to grow and grow and grow. So what we need to do is find a way to consolidate the information into a way that we can use. That's the job of the pooling layer. Let's take a look at what I mean by the number of parameters is going to grow and grow and grow to this point, and then we'll reduce the size of it with a pooling layer. And then we'll make it grow some more, and then we'll reduce the size of the pooling layer. What's going to happen is we'll increase the size. Remember, we had channels for red, green, and blue. Well, later on, the channels are going to be in the features. And what's going to happen is that we're going to increase the intensity or the size of the features, and at the same time, we're going to reduce the size of the input data, which is, in this case, 32 by 32. I know that's confusing, so let's take a quick look at what I mean. Okay, so here's what I mean. I'm going to say cfar.build model, and I need to pass this a shape, right? So maybe I have I have a batch of maybe 100, and there are 3 channels, red, green, and blue, and then 32 by 32 images for the pixel size. Okay, so look at what's happening here. Every time that I hit a convolutional layer, I marginally drop a little bit of data on, coming down from this 32 by 32. And the reason is that the searchlight beam that we're shining has a width to it. Maybe in this case, it's 2 elements long, so the beginning of the searchlight is not going to go all the way across. We're going to lose a little bit of size here, but not too much. But look what happens to the number of channels. I go from 3 to 32. This is a lot more data, and I can't continue to grow and grow this all the way through the network, or I'll wind up with some numbers that are unmanageable and performance that's just too slow. So what do? With a normalization layer, I make sure that the numbers stay stable. So in much the same way that I divided everything by 16 times 16 to keep the numbers between 0 and 1, this normalization layer does a similar job. But the other thing that I do is I go through this pooling layer, and look what happens. I have my batch of 100 that's going through with 32 channels, and it's 15 by 15 coming out of this layer. So what's happened is that we've cut this dimension in half, and that's a very good thing in terms of performance. So what we're going to do now is we're going to take a tensor that is, let's say it's 8 by 8. But remember, we have a batch and we have channels. Let's say that this is a black and white one so that there's just one channel. And I'm going to pass this through nx.iota. And then I'm going to see what I get. You can see that this just counts. But if we scan a searchlight, maybe the first one covers this square right here from 0 and 1 to 8 and 9. And if I'm trying to pluck out the maximum number, I'll get 9. And then the next square, if it's 2, 3, 10, and 11, I'm going to pluck out the 11, and so on and so forth. I'll pick out the biggest number, which turns out in this case to be the lower right corner of every square. And how do I get that? Well, I use the layers again. Let's say axon.layers.max. And then I'm going to have to pass this thing a kernel size, right? And the kernel size is the size of that square. Well, let's say, what if we had a size of 2 by 2? So that one square is 0, 1, and 8, and 9. So let's say 2 by 2. What does this give us? Okay, look at this. So I get that 9, and then I get the 27, which is the lower right of this, or the 25, which is the lower right of this square, and then the 41, and then on and on and on. And let's see what these two things look like, if they look similarly in heat maps. So I'm going to take this one, and I'm going to pass it to nx.to heat map. And I'm going to take this one now. Aha, look, it captures the essence of the image without actually being the same image itself. It's a smaller size, it's 4 by 4, but it still captures the essence of what's going on in the image. It's almost as if this pooling layer were pixelating the output. And if I want to, I can pixelate in bigger increments, right? So I could pick a 4 by 4 searchlight, if you will, that scans across in big chunks. And this just gives me 4 different colors. And so if I take that out of the heat map, it looks like 27, 31, 59, and 63. So let's look and see if we're getting what we expect to. So this is a 4 by 4 square. 1, 2, 3, 4. 1, 2, 3, 4. So the biggest number out of all of this square is a 27, and that's what I got. And in this one, it would be a 31, and that's what I got. And 59 and 63. So I really catch a pretty good approximation of what this whole thing is, right? So this is a game of give and take. When we look at the model, I'm picking up information in terms of more features, more channels, if you will, and I'm giving up information in terms of the resolution. I do my image processing, and then I flatten things so that I can process a linear regression, dropping out some of the data in the middle so that things work in a more general way rather than being fit only to the training data that I supply. And that's an excellent thing. From Bruce and the dog on the floor, this is Gruxio Learning.